Here's a question that might come up in an algebra class. You're doing some work and you get some final answer that looks like this, which looks really scary. And the question is, please make that look friendlier. All right, you look at this and you realize, okay, we've got lots of fraction stuff going on. We've got the fraction 1x, whatever x number x happens to be, plus 1 as a numerator, and we've got the fraction 3x, whatever x happens to be, as the denominator. And I admit that looks pretty unfriendly right now. But we can make it look friendly by just doing the same work we were doing before. All our work so far has been with actual numbers. Even if x just represents a number we don't know, these are still actually actual numbers, just we don't have to know what x is. But all the mechanics we did before applies to that as well. So it seems irresistible that say, I don't like all these x's on the top and the bottom. What if I just use belief number 4 and make my life easier and multiply the top by x and the bottom by x? Then I can see, if I do use the standard distributive rule, 1x times x, that's this one, will just be 1, plus 1 times x. Bingo, there's the numerator, and the denominator, 3x times x, looks like I'm using x and x there, I'll just get 3 as a result. Oh, I think that looks friendlier, I'm going to stop there. 1 plus x over 3, much friendlier indeed. Okay, that was fun. Let's do another one. Let's work out this. Suppose you're doing some algebra problem about some numbers a and b, and you're actually told what the values a and b really are, but you know they're numbers. And you get some work and you get to this final stage, 1/8 minus 1/8, all divided by ab. That looks pretty complicated. So maybe you want to make that look friendlier. What could you do? All right, so these are numbers. You just don't have to know what they actually are, but they're numbers, which means everything we do with fractions applies to this. And I look at the top and I see eighths. I don't like eighths in my numerator. I also see beaths in my numerator. I don't like beaths. So let me handle making the eighths and beaths go away in some sense. And the way we were doing that all along was multiply the top by a should handle the eighths. And I want to handle the beaths as well, so I might as well multiply the top by b as I go along. Now I can't just change the top, because I need, by belief number 4, if I change the bottom as well, then nothing's changed. That's still the same quantity. Bingo, that's the same quantities I started with. Hopefully that will actually help me out. Now I'm going to go a bit fast here. I'm going to assume we're totally familiar with the mechanics of fractions at this point. But right now, if I do the distributive rule, I see 1/8 times a times b. The a and the 1 over a will cancel, just leaving me a b all by itself for the first part. Minus 1/8 times a times b. And you see the b's will cancel there, leaving me just an a on the top. Bingo. That's the numerator. And the bottom is, well, I don't think I can do much with the bottom. It's still a times b times a times b. So it's an a times an a times a b times a b. It's an a times an a times a b times a b, a squared times b squared on the bottom. So there I think this is a bit friendlier. I suppose it is. I mean, I guess the term friendlier is actually subjective. What looks friendly to you might not look friendly to me, and vice versa. But I think maybe that's actually a bit of help. At least I don't have fractions in my numerator of my fraction. Okay, that's a good thing. Okay, let me do a third example like this. This one actually causes a lot of worry for many students. Please make 1 over s to the negative 2 look simpler. Okay, people get really confused about negative exponents, but let me just write out what a negative exponent really is. I'm looking at 1 over s to the negative 2. That is 1 over the quantity 1 over s squared. Because negative exponents are the inversions of the positive versions of the exponents, if we know our exponent rules. So now I've got a fraction with a fraction as the denominator. And that seems awkward unless I invoke belief number 4 and make it look simpler by multiplying the top by s squared and the bottom by s squared. Because then on the top I'll have 1 times s squared, and the bottom I can see the s squareds cancel to give me 1. I can now see this is just s squared. Beautiful. So I don't actually have to memorize any rules about what to do with negative exponents on a denominator. I can just think my way through it and see, oh, it's going to be s squared in this particular case. And I agree, that looks friendlier than that. That one is definitely a good one. Okay, let me end today with one serious source of confusion for many students about quantities like this. 3 plus x over 2 plus x, say. Now, people say you can just go ahead, split up the numerator. Think of this as 3 over that denominator, 2 plus x over that denominator, 2 plus x. Just split up the numerator, all should be fine. Well, if you just split up the numerator then, it says, well, maybe I can just split up the denominator as well. Keep that as the same, keep the 3 plus x, but split up the 2 and the x here. Same 3 plus x, but now over 2. Same 3 plus x, but now over x. All right, what I want to do today is actually question both of these. What's going on? Are they both correct? Is one correct and neither correct? Let's think our way through it. So let me go back to the beginning of fractions. Now, if I take a quantity like a over n, now we actually, by this multiplication rule, where is it, this one, you can actually think of this as a times 1/nth. A times 1/nth, which actually, let me remind us of everything. That is actually bringing together all the ideas. A nth is really a copies of 1/nth. So back in our copies of version, that's what that's really saying. It also matches our names. Remember, that was called the numerator. Numerator means numeration, to count things. That was called the denominator. Denomination means the type of thing. We're actually counting a copies of this type of thing, nths. So this is actually a very lovely rule. It explains what's going on with fractions. A nths is really a copies of 1/nth. The language we use, numerator, count of, type of thing, fits as well with that mechanics. Great. I will invoke a little multiplication is commutative idea. I can think of this 1/nth times a if I prefer. But I'm going to do that just because it's just a little bit easier for these guys, which have a very complicated a. A is all this, 3 plus x, and a very complicated n, 2 plus x. So let me actually look at this. Well, okay, keep this in your mind. This is what I'm about to use on this visually complicated version of that. Here goes, here goes. So I'm going to play with this. 3 plus x over 2 plus x. That's my a, that's my n. So what we just did, that's the same as 1/nth, 2 plus x, 1/nth times my a, 3 plus x. Beautiful. So just playing with the mechanics of fractions, that's what this quantity is. It's that. And now I look at this and think, okay, well, okay, I've got a little rectangle here. I can see I've got a rectangle that's 1 over 2 plus x high, and it's 3 plus x wide. Oh, so I'm going to do the distributive rule. I'm going to do 1 over 2 plus x times 3 and 1 over 2 plus x plus x. That is, I can say this is equal to 1 over 2 plus x times 3, times 3 plus 1 over 2 plus x times x. Okay, getting messy and scrawly, but look at that. 1 over 2 plus x times 3 is 3 over 2 plus x, and 1 over 2 plus x plus times x is x over 2 plus x, which is this. This is that one there. That is actually correct. That is actually correct. In fact, I could have seen this correct if I actually did call this n all the way along, because that is actually our rule for adding fractions with a common denominator. Oh yeah, 3 plus x nths really is the same as 3 nths plus x nths. Beautiful, beautiful. So yes, that first quantity is definitely so. All right, but this second one's got me worried, because nothing I did here showed me how to split up that 2 plus x. It's really 1 over 2 plus x. It makes me, there's nothing here telling me what to do about this one. So I don't think I had any choice in what I did. I can't think of anything different to do to try. So I'm now wondering whether there's any reason to believe that, because the math's not giving me any reason to believe it. And now I've got doubt in my mind. Maybe we should just check it. And people forget in algebra class, x can actually be a number if you like. I'm going to let x be a number and see if it's true. I'm going to choose a pretty easy number. I'll choose like x equals 1. Then the left side would be 3 plus 1, 4, over 2 plus 1, 3. The left-hand side is 4/3. The right-hand side will be 3 plus 1 is 4 over 2, 4/2, plus 3 plus 1 is 4 over 1. This is what? 2 plus 4. This is 6. There's no way that 4/3 equals 6. There's no way that 4/3 equals 6. This is not true in general, because it's not true even for x equals 1. That cannot be true. The maths had nothing to say about this, and therefore I had no reason to believe it, and it turns out it's not going to be true. At least in this one case here and in general. Whoa. So here's the thing to think about. This is where the language of numerator and denominator are really good to keep in your mind. It kind of makes sense. You can actually split up counts of type. For example, I've got a things plus b things of the type n. So there's my numerator. I'm actually focusing on the numeration of these things. That really does feel like it's a things of type n plus b things of type n. I can split up the numeration. I can split up the counts. That makes good sense with my intuition here. And actually, when I think about types, when I think about denominators, it doesn't quite make sense to me that I should be able to split up types of things. For example, I've got a things of type n plus m, some big number there. I don't see why that should be related to having a things of type n and also having a things of type m. There's nothing in my sort of intuition says this should have any connection. So keeping that numerator, denominator thinking language in your mind can help out. It's very natural that we can split up counts. In fact, that turned out to be true and correct, and we had the whole big sprawly math to justify that. And I don't suspect there's any reason I should be able to split up denominations, the types, and I could see no math that would even lead me to that, and I even saw that was actually wrong with an actual numerical example. Oh, so that is very subtle and confusing, and I completely understand why students would be completely confused by that, because it takes a lot of deep reflection to see what's going on there. That was a tough one, but thanks for hanging in there.